Hello everybody, 6 p.m. at PST. Let's get started. There are 12 total. Maybe let's wait for a couple of seconds or minutes to make sure everyone comes in. Did I start the recording? Yes, I started. Okay, so our topic tonight was this thing or division, logical division circuit. Hope you have reviewed that one. Any question from that part? Let me check the discussion if there is any. No, I don't see any on the discussion side. Okay. So you guys are working on the project. Hopefully after tonight, you should be able to finish up the project implementation on the logical division side. And then, then also write the report and you'll be done. I think you have exactly a week to complete the whole thing, and submission is on April 26. That's not my bad. May 6. May 6, right? Just make sure. Yes. May 6 is the deadline for the project. Any question from anything else? No question from division circuit? No. On the project side, everything going smooth? You guys are really quiet tonight, seems like.
Professor,
Yes, Rahul?
could we discuss the working of a left barrel shift tree after the division circuitry recap and stuff?
Left barrel shifter. It's not even part of our course, basically. Yeah. Are you asking out of curiosity?
I'm asking because the pop quiz had a question on it, and I was not able to understand it. I didn't understand what to reference in a previous material.
Popquiz has that question? Oh, can you please send me an email? Probably it's by mistake. I need to check. You should not have
Or
any
I'm
question.
actually double checking the quiz right now just to make sure I got it correct, or I'm not put using different words.
Yeah, because barrel shifter should not be part of your curriculum. Yeah, at least not part of that. So
Yep, it is
yeah, if the quiz
barrel
have,
shifter.
okay, please send me that. It's
All
probably,
right.
yeah, probably kind of a mistake from my side to include that question on the quiz. So we'll be studying about barrel shifter in next course, 147.
All right. All right. By the way, professors, your lecture videos on YouTube, they cannot be searched up on YouTube, can they? Like the listed is unlisted, right?
Mm, there are some tags, but not really searchable. I don't know. Like, what do you mean by that? Like, you are searching by title or what?
Or I was just curious about what's this publicity setting of the lecture recordings, and not lecture recordings but the live class, because I just noticed after the last class
Uh-huh.
you started with your next class and you were having a quiz in the next class, and that class showed up in my recommended like 30 minutes later with when the quiz was active in a different class.
Oh,
Yeah,
okay. Yes,
just
I
thought it's
don't.
interesting, thought I should let you know.
Okay, please. Yeah, can you send me an email with what you observed? I couldn't quite get fully probably what
Sure.
you observed. Please send me an email. I need to check the setting. We usually have both the class streamed. Yeah, it's streamed live, and also it's being recorded on the YouTube live, both 47 and 147. I'm not sure what happened. Something happened maybe. Yeah. Okay. So on the division side, division is the interesting operation, and we usually have the sequential way, like in next course, like 147 course, you'll see there is a way to make a combinational multiplier. We'll implement that actually next course. But for division, uh, it's okay. It's not practical to make a combinational division circuit. That's what I can say to you. It is theoretically possible to construct a combinational division circuit, but it will be really, really a slow circuit. And for all practical purposes, people go with a sequential style of division operation. Um, the reason behind that, mainly because it needs that rollback operation. Like if your subtraction goes other way, you need to roll back to the previous result, and that's why sequential is a preferred choice to implement division operation in the logic circuit. And also another point to note for both multiplier and divisor, you see that the core one is basically unsigned multiplication, unsigned division. And then we have circuit on top of that, on around that, to make it a signed multiplier or signed division circuit. Make sure you understand that part as well. So main philosophy is that whatever sign your input might be, my input operand might be, you change it to unsigned bit pattern, apply uh, apply the unsigned uh, circuit on top of that, like make the data crunch through the unsigned multiplier or unsigned divisor. And then on the output of the unsigned multiplier or divisor, then you decide what that result sign would be depending on the operand sign. So that's the whole philosophy in that construction of that logic circuit. So make sure you understand that part as well. Okay. Anything else important to note on that? Let me see. So you guys probably noticed that this division circuit, especially the simplified division circuit, has applied one pretty complex type of register, 64-bit register there, where it basically have like all the features like parallel load, shift right, shift left, all of them together uh, to make that 30 make the division 32-bit division happen only using a 32-bit adder subtractor circuit. So that's the one another interesting thing I want to mention to you guys on that. And also make sure you understand that sign conversion in the sign division circuit. Uh, it is one part, it is very similar to the multiplier sign detection, which is an XOR, applying an XOR logic between the dividend and divisor operation. That is for your quotient sign, but remainder sign is always same as the dividend sign. That's what are different from the multiplier. Multiplier sign is solely that XOR operation determine that the entire sign of the result. So basically, division makes like two results. It's a one result is quotient, another result is remainder. Whereas multiplier produce one single result. It's from 32-bit multiplication results in 64-bit result of the multiplication. Okay. All right. Um, what else? Like I don't have any much to discuss tonight, and I was planning to just let you go early to so that you can start or continue work on your project and complete it by your deadline. So tell me what else you want me to discuss tonight.
Professor,
Yes, Aditya.
when will we set up like review sessions for the final, or will we do
Review
that?
session, I think there are two review sessions. I think one is on May 11, another is May 13.
Okay.
Okay. Yeah, after next two classes.
Okay. Thank you.
Okay, so let me do this polling on your project status. You can make it anonymous, anonymously answer that. Let's see where are we in terms of class. Take a minute to please answer that.
Professor, I actually had a question.
Yes, Ricky.
So for the addition, subtraction, logical implementation, I know at some point we use like XOR or XOR in the process. Are we allowed to use the MIPS command XOR for it?
Yeah. Yes.
Oh, okay. Yeah, just making sure. We're just not allowed to use like the MIPS add, subtract, and all that, right?
Exactly.
Everything else is fine.
Yeah, everything else is fine.
Okay, just making
Even
sure.
for if it is for your index, like in a loop, if you want to increase the index, for that purpose you can use add I.
Right.
Just don't use add, sub, multiplier, and division.
All right. Cool. Thank you.
Okay, I think all of you guys have voted. Let me share the result. Okay, a majority of you have completed the normal ALU, 71%. Logical addition, more than 50, more than half. Logical subtraction, okay, 30% of the class. Logical multiplication, 18%. Logical division, 12%. Okay. Most interesting is that four of you have stated you haven't started yet. Please, I think this 1 week you probably spend all the time on this project. I hope so. Okay. Yeah, for others who are still struggling with the addition, subtraction, that part, please make sure you complete it because you need to reuse those, you need to reuse that procedures in your multiplication and division. So unless you make sure your addition subtraction works fine, your multiplication division won't work properly. And my recommendation would be, maybe it's a very late stage to recommend, but test as you implement. Don't wait for testing till the end when you have coded everything. Because since this is an assembly program, you don't have much help like a debugger or things like that to debug your program if you run into problem. My strategy would be always code a little, maybe okay, complete the logical addition and test it. Addition is working fine or not. Then do the subtraction and test it, and then multiplication, test it. So test at each and every step as you implement. It can be very like small, insignificant, little bit of change in one part of code that can affect your result entirely, unlike high level language. So that would be a very tricky situation if you start testing at the end of implementing everything. So make sure you do test stepwise. Okay. All right. So after these, there is two more lecture coming up, which is kind of miscellaneous, and we'll just touch upon, not go into not much details on that. One is the floating point representation, how the floating point values are represented, fraction values are represented inside computer, and what are the associated instruction and hardware resources available in the processor. That's what I think the next day's lecture is about, this floating point number representation. So we'll study that in kind of a very theoretical point of view. We won't do much programming on it. Maybe we will look at some example, an example, I would say simple commands. And you will see there are two types of floating points command. One is the single precision floating point command. Another is a double precision floating point commands. Make sure you can point out those instruction in the MIPS green sheet. Okay, I think you will find out on the first page of the MIPS green sheet on the right hand side top corner. So it lists all the floating point instruction and all the list of the register for that used to store the floating point values in a component called a coprocessor, floating point coprocessor. What it means actually in reality, it is basically a processor which is not inside the main processor, but it is something different. It's just that specific floating point processing unit is not part of the main processor of MIPS, but it is somewhat staying external, conceptually external to the MIPS processor. MIPS native processor capable of only integer operations, whatever you are implementing right now, those operations. For floating point operation, it's a different processor and it has all set of different registers and stuff like that to manipulate the floating point data. Interesting story behind that is when computers first started, right, there was no hardware component that used to evaluate floating points. Okay, all things are integer operation, integer addition, integer multiplication, division, subtraction, etc. And software libraries used to have that floating point manipulation algorithm based on the integer operation. Okay, so all these software libraries used to have these floating point manipulation libraries, and these floating point addition, subtraction, multiplication, division was part of APIs of those software libraries. But as the hardware technology progressed, and then it was possible that we can implement those software algorithms as a part of the hardware. So basically, this floating point coprocessor is nothing but implementing those floating point algorithms on silicon. In fact, one can actually implement any algorithm on hardware directly if it is kind of defined in that way. Uh, people Why people doesn't do it for everything? Because of the business value, like how much value you will propose to make it an hardware component to implement one certain algorithm. So that's the question there. So you will find there are many applications like for example, nowadays this graphics processing, right? Graphical processing libraries used to be part of the software, but nowadays it has become part of the hardware in terms of GPU, graphics processing unit. So what it does, practically what it does internally is a very fast matrix manipulation. So if you take graphics class, you'll see all these graphics theories and everything, they revolve around this basic operation on the matrix. and GPU actually provides mathematical operation on the matrix as a hardware resource. So those algorithm was into the GPU. People have seen that, okay, there is a market, there is a business, and it is worth to put it on a piece of hardware to accelerate and make it a faster graphics rendering and stuff like that. So that's why it was put on the specialized hardware. I believe what I heard in the Google, some of the searching algorithm also has hardware component in it, and they actually run directly on the hardware. So it's interesting paradigm there. In fact, like what I have seen, like time to time, people actually switch back and forth between software and hardware wherever it gives the edge. For example, network switch, right? You know that network, there is this hardware on the network, like for the network communication, which is called a switch for the packet switching purpose. But nowadays, people actually trying these software switches, like software network switches, and there is some potential to actually build up uh, uh, build up the switches using software and using a generic hardware instead of building a specialized hardware, so that it can cut on the cost without cutting much cost on the speed side. So it's always possible that one problem can be solved with the software and the hardware, and depending on what is needed, what is desired for the market, and what is the target goal, industry decides that whether, well, I want to go with a specific specialized hardware to solve that problem, or I use a generic hardware and implement a software on top of that to solve that specific problem. So that's very interesting thing to study and thing to think of. I just wanted to give you a very like sneak peek of those areas that you might want to venture around and see what is going on. Okay. All right, then if we don't have any other question, then we can stop tonight and go back and continue work on your project, make it done, and then see you on next Tuesday. I'll wait for maybe another couple of minutes to see if there is any question from anyone. No? Then good night, everybody. Let's stop tonight early. And please continue working and completing this project.
Professor,
Yes, Kevin?
for some reason, I'm getting this error often where I get a runtime exception because it says that the address is out of range.
Usually what I have seen, it's due to not having that store restore control properly, because you guys are basically interacting with my part of code, right? And if you are not very strict on those store restore part of the frame, people usually run into that kind of problem.
Okay.
Your procedure has store restore exactly like the theory what we actually learned. Don't try to make any shortcut there. Okay, and if you can shoot me an email if you still see there's a problem, and you can work with your study group, help each other, take help from others to like see what's the problem. Okay, Kevin, is that fine?
Yeah, thank you.
Professor?
Yes, Rahul.
Yeah, I had two small things to confirm. First
Sure.
thing was the MIPS does not provide any kind of random function or something like that, right? Random generator.
MIPS does not provide it. No.
Okay, neat, neat. And the second thing the only difference between the universal logic gates and the fundamental logic gates is that fundamental has an inverse gate, but universal does not.
Yes, you can say in that way. So I'd think in a different way. Fundamental logic gates are the logic gates which we can fundamentally implement with on the silicon, right? Okay, so you'll see in the next course 147, the fundamental building block of any logic is called a transistor. Okay, and by combining transistor we can build up complex logics, and when we do that we practically comes up with something like inverter structure or NAND structure or NOR structure. Okay, there are specialized structure for other specialized circuit. That's the different point. But in general, these three are the fundamentally we can build with electronic component. Whereas universal logic gate, I would say it is a fundamental logic gate using which you can build up any logic. So
I see.
yeah, so it's kind of an like that perspective different. I suggest you to make that perspective.
Wait. So just to be clear, as far as implementing on silicon, it's more general to implement the NAND and NOR than AND instead of AND and OR.
Yes. So on
Okay.
the silicon, if you look at the AND gate, you will see that circuit is nothing but a NAND and a NOT gate combination. You cannot build an AND gate directly.
I see. All right. That's one misconception cleared. Thank you, Professor. See you
So,
next class.
all right. Anyone else? Anything else? No? All right. Let's stop.